Okay, so the first one is me. The other two people are already famous. They don't need any introduction. This presentation has something to do with trees. Okay, so let's go. So we have a classification task, right? And we want to generate some tree like this. Okay, so a tree has basically a bunch of nodes. Each node has some question in it, right? And those questions are based on the features of the data set. And we want to generate this kind of a tree. Right? So we'll call these questions, I'll call this as split checks. And yeah, the leaf nodes also have some targets in it. Okay, so the easiest way to generate this kind of a tree is by using machine learning card algorithm. Right? So it's a very fast heuristic algorithm, which it basically works off all sorts of data sets, and once you give that data set, it will just spit out a tree like this. And so very fast and heuristic, but as I said, it's a heuristic, so it doesn't really give you the optimal trees, right? So in whatever way you define your optimality, it doesn't give you the optimal trees. Okay, so not strong. And people in OR community don't like that, and so they came up with a lot of different types of models, MIP models, CP models, SAT models, all sorts of models. And sometimes they do give optimal trees, but they are not very scalable, right? So they only work with like very, very small data sets. Don't work well with when your data set is like super huge, or trees are like say super huge. But that's the life. Yeah. So really recently, Firat and other people came up with another heuristic, which is based on column generation. Right. So it gives up on optimality. That's why it's a heuristic, but it is more scalable in terms of it can handle larger data sets. And it is more accurate compared to what the card provides, right? So some heuristic which gives you this kind of a tree, right? So let's actually take a look at what those people did. Okay. So first of all, let's actually define the problem statement, right? So they didn't work on the very proper problem statement. So they said that we will not consider all possible split checks for every node, right? So they said like we will restrict our attention to some candidate split checks for every node instead of like working with all possible split checks. So that's precisely where they lose optimality, right? So because of this, the trees are not optimal. But it is not super bad. Okay, so let's actually even take a look at how exactly they come up with this candidate split checks, right? It's like the beginning of the problem statement. But so yeah, they basically start with the data set, right? Training data set. They select a portion of this training data set, right? Say random portion, but fairly huge portions, 80-90% portion, and then they give it to the cart, right? So cart will come up with a tree, and that tree will have some split checks on their nodes, right? And those split checks are basically added to the candidate split checks. It's a very simple process. You just repeat it a bunch of times, and you'll have fairly reasonable candidate sets on which you want to optimize, right? So the tree topology is kind of fixed. Okay, so depth of the tree and what kind of nodes it will have, it is fixed. But and the other things like the candidate split this is how they generate it, right? So now the question is that given these are the candidate split checks for every node, we want to select the best split checks and for the internal nodes and the best targets for the leaf nodes that will maximize the accuracy on the training set at least, right? So that's what they do it with column generation, right? So consider a path from root node to leaf node, right? And when I say a path, not just consider the nodes, but also consider an individual split check assigned to that node, okay? And also one target assigned to the leaf node. So this makes one path, and they have one binary variable for each path. And you can see like basically like there are exponentially many paths, so that's where you get the column generation part, right? And so obviously these variables are generated using column generation, but let's actually take a look at the entire model, right? So there are so those were the key idea of the column generation based heuristic. So that's the kind of variable you want to have, but the constraints are basically very simple, right? So first is that for every leaf, like there are many paths landing in that leaf, and we want to select exactly one of those paths, okay? Second is that for every row in my data set, it satisfies bunch of paths. When I say satisfies, it means it just follows that path. It may not be classified correctly, but it is just following that path. Okay, and we want to select exactly one of those paths that are satisfied for each row. Right? So like basically, what they're trying to say is that the rows should not be like classified in an ambiguous way. So that's the thing. And the last constraint is that if I have multiple paths selected, then they should basically agree on the common nodes, right? So at least the root node is common in all the paths. So they should have the same split check at the root node, and if there are multiple common nodes, then they should have the same split checks assigned in those common nodes as well. Right? So very simple things. And the objective, they didn't really experiment much. They said just maximize the accuracy on training set. Right? You can actually do a lot more things than just maximizing accuracy on training set. Or you can actually, try to focus on making trees which are more, general, like that the performance is generalized and everything, that works well on test sets and everything. They didn't do it, and so I'm also not going to do it, right? So that was the master problem. Sub problem is kind of easy, like you just take the duals from this, compute the reduced cost expression, and just maximize that reduced cost, right? So we are maximizing accuracy, so reduced cost, we just want to maximize it. And I'm not really going to even describe the constraint. So the sub problem is that we are trying to generate those path variables, right? The constraints basically ensure that every time I generate a path, the accuracy of that path should be correctly computed. That's all the constraints are about, right? You don't really need to know the details of the exact constraints. The important part to notice in this subproblem is that there is one subproblem for every leaf and every target. Okay, so in this particular example, so we have 4 leaves, 2 targets. That means 8 subproblems. Okay, and they didn't do any branch and price, so we are also not going to do any branch and price because it's kind of too expensive. So they solve the root node with optimality, with column generation, and whatever columns are generated, they will just use that and give it to the integer programming solver, and that's like they output the final tree. Okay, so let's now. So this was all what Firat and other people did. So now our work starts. So first improvement or contribution is that we moved the target computation inside the constraints. So now we have one subproblem for each leaf. Okay. So previously we had 8 subproblems. Now we have 4 for this example. Okay, and this is not free, of course, right? So when I move this target computation to the constraint set, it basically means that I have extra constraints and extra variables, right? So larger subproblems. So it's not super clear whether it is going to help me or not, but we'll see that at the end. Right? So this is the contribution for which kind of motivated us to start the project, and then more things came up on the master problem. Okay, so in the master problem, some of you might even notice that these constraints are kind of suspicious, right? So they are kind of data dependent constraints, and why I'll not give you the proof that actually this constraint can be derived from these alpha and gamma constraints, but I'll rather share you the intuition which made me think that why these constraints are suspicious. So let's start with some data set, let's say, right? And let's say I selected the first half of this data set for my training, okay? And I gave it to this column generation heuristic, and this is the tree that heuristic came out of, right? So every node has some selected candidate split, and leaves have targets selected in it, and then I evaluate the performance on the testing data set, let's say, right? And let's say I'm not happy. Yeah, I just selected 50% of the training data, and I'm not happy. This training data sets, right, the rows in the training data sets, they are being classified, but they are not being classified correctly. So let's say I tomorrow change my mind and I just moved some of these testing data sets to the training data set. Yeah, it's not a good thing to do, but yeah, I did it anyways, right? So for the purpose of this argument, and so this tree that I had generated before, right, it is no longer optimal tree. Right? Because now I have more information about how to classify these extra rows, right? So they were being classified, perhaps not correctly, but now I have more information. Now I can look at their targets as well and everything. But the thing is, this is still a feasible tree, Okay, so these rows were being classified before, perhaps not correctly, but they were still being classified. And that was the purpose of those beta constraints. Like those rows should not be classified in an ambiguous way. So that was the constraint. And these rows were classified before. So this rows should still be classified, even if I just move it to the training set. And that basically means that every row in the training set, which I even had it before, right? They were being classified regardless of whether I add those beta constraints or not, right? So the easiest thing we can do is that just simply remove those beta constraints, and we quickly found out that it leads to poor LP relaxation. So what's the second best thing we can do? All right, so we decided we'll add them as cutting pins. Okay, so we'll keep them aside, and if at all they get violated, then we will add these constraints to the master problem and see how that works. Right, and so this kind of started working well for now, and this now brings a question. Now it's like this kind of design for this master problem. Right? So it says that the strength of my model, how strong the LP relaxation would be, it depends on what kind of data set I have, right? Because these beta constraints are kind of for the data set, right? So if somebody gives me a very bad data set, then my model might not give very strong LP relaxations, and that's something that we don't like, right? So the strength of the model should depend on its design, not on the data set that I get. Right? So the question that we started asking was, can we actually generate these constraints even if the corresponding data points are not there in our original data set? Right? So we did that, and there is a SAT model, and if you are obsessed with MIPS, then it can be linearized. Yeah, so it's basically it can generate this kind of a beta constraint even if your corresponding data point is not there in the original data set, right? So I don't really need to generate the targets. I only need to generate the data points. And I'm not sharing the entire model, but the key idea is that you don't really need to generate the entire data point, like values for all the features. You just need to decide what that data point will do on each candidate split check, right? Whether it will go to the left or right, and just decide that based on the way you want to maximize the violation of this constraint, right? So that's one more contribution. Okay, and so that's kind of pretty much all for master problem, right? So we saw something about subproblem, master problem. So let's bring our attention back to the way we generated this candidate split checks. Okay, so we selected some data points and gave it to cart, and cart generated a tree, and then we were just adding those split checks to this our candidate set, right? So this cart is actually generating this entire tree, right? So these are not just the split checks that we should be interested in. These split checks actually make some very good paths itself, right? So this cart is actually giving us some good quality paths. Cart is a heuristic. They're not really good optimal paths and everything, but they are still like good quality paths, and we can actually use this extra paths for initialization in our master problem, right? So that's one kind of minor. These are like minor engineering kind of things. It's not a very strong theoretical contributions, but yeah. And the other thing is that it's very annoying, but like if you have some data points, right, and they have, let's say, same targets, they're not exactly same in terms of features, but let's say if they are exactly doing same things on all your candidate split checks, right? So for the model's perspective, like if they're basically like going, both of them are going left on certain splits, or both of them are going right on certain splits, and pretty much the behavior is same for all the candidate split checks, then they are, for the model's perspective, they are the same, and you can basically remove some of them, right? So when you remove one of them, like you have to increase the weight of the other one, because otherwise you'll mess up the objective and things will break, and you will discover that after a few months. But anyway, so this is something. The point is, like, just because they give you a large data set doesn't mean you have to solve large problems, right? So you can make your problem smaller just by doing some trivial engineering things, and this sometimes works well. Okay, so pretty much now let's take a look at the results. Okay, the data set, it's been running around for a while. So Firat and other people also use the same data set, and one paper before that also used the same data sets, and it's been open sourced and everything, so exact train test splits are available. So we are also using that same data set, and everything that has less than 10,000 rows is small, everything that has more than 10,000 rows is large. And in Firat and other people, they basically claim that other than column generation heuristic, no one is able to handle these large data sets. Right? So pretty much all MIP models, CP models, SAC models kind of fail at handling large data sets. But they can do it, and so we are just going to slightly improve their results. Okay. So the first thing that we did was merging the subproblem. Right. So when I do it with some time limit and turn off all heuristic ways of generating paths, then it actually results in slightly better accuracies over card, right? And the reason for this slightly better accuracies is because this merged subproblems are faster than original smaller but larger number of subproblems. Okay, so you can see that in the second graph, it's like it results in more column generation iterations for the same time limit, and that's why you have slightly higher gains over cards compared to the original cards, right? So now let's come to the beta constraint, right? So there are we found like 6 ways of using beta constraints. So one is like don't use any beta constraints, which what we did first, and then 3 ways of adding these beta constraints as cuts. So one with equality constraints, one with just the upper bound, one with just the lower bound. The next variant is all beta constraints, which is like the default version which has been there. So yeah, that's what Firat and other people did. And the last one is where I generate the additional cutting planes, right? So even if the things that are not in our data set. Okay. So I'm measuring the solving time, no time limit now. So the first 2 variants are fastest, but we'll see in the next few slides that it is actually those variants will give you basically the lower, bad LP relaxations, and that's why it will result in comparatively lower gains over card. The other next two variants, the beta constraints as cuts with upper bound and as equality constraints, are kind of the best shots. Like they give us like a reasonable solving time, and they are like always smaller than using all the beta constraints in the master problem at the beginning, right? And the generating cuts part is like the slowest, right? So one is that SAT problem, right? It's an integer program, so it takes time to solve. And second is that when I add more cuts, it takes more column generation iterations to finish, right? So that's solving time. Now let's take a look at the LP relaxations, right? So the first 2 variants which finish the fastest, they give you the worst LP relaxation. The other 4 variants give you like something similar. Like it's kind of hard to notice from this graph that which one is better, but there are differences. Okay, but clearly like the first 2 variants are the bad ways of doing things, and they also result in slightly lower gains over time, whereas the other 4 variants are kind of same. So for the other 4 variants, we care about the speed, and the speed wise, the third and fourth one was the best. Okay, and you might ask like the generating cuts might be stupid idea to do, but if you care about optimality, right? So when I say optimality, it doesn't mean like generating optimal trees, because we gave up on optimality long ago. But let's say in this problem definition where we are restricting our attention to this candidate split checks, and from this candidate split checks we want to generate the optimal trees, then it turns out that this generating cuts is kind of a good idea. So these were like 55 instances, and out of 53 of them it could generate the optimal root node relaxation. Right? So when I say optimal, it's because like I also found integer solutions with the same objective. Right? So we don't really even need to do branch and price if we have just these generated cuts. Okay. So the last one is pre-processing and initializing the engineering effects. Right. So one variant where everything was on, one variant where pre-processing was turned off, and one variant where extra initialization was turned off. It's always bad to turn off extra initialization. The gray lines are always bigger than blue lines, and the pre-processing is not so clear. It's like it is better on all the smaller data sets, the ones which are on the left side, right? So the pre-processing doesn't work very well on the smaller data sets. It kind of makes things worse, but it's always beneficial on the larger data sets, right? So it's always better to reduce your data set first, like remove some duplicate rows and everything, and then jump to the column generation. So like putting all those things together, the direct comparison, now there is a time limit of 600 seconds, 10 minutes, and this is the one on the smaller data sets on the training set. I recall that we don't do anything about testing part, right? So we don't do anything on generalizing part. So always accuracy gains are like slightly higher compared to the original column generation approach because of this modifications. At the larger data set, they didn't have the data on the training set, so we had to measure effects on the testing set. Okay, so again, like we didn't do anything to generalize the performance on the testing set, but it is still like, and so that's why like there are lots of zeros, right? So gains over cart is like not significant, but so like specifically like look at the letter recognition data sets, right? So there are still like sometimes reasonable gains over cart. So yeah, I think that's it. So we improved sub problem, we improved master problem, we improved something to do before column generation. So yeah, we improved basically trees, right? So yeah, Montreal people can relate to this image, right?
Maybe not everybody.
No?
That was what, a month ago?
Yeah, so Montreal, it was in Montreal definitely, right? So yeah, that's the conclusion. We improved trees, but we didn't solve global warming, right? So yeah, time for questions and suggestions, and yeah, when you move to different machine, then they have those two letters were supposed to be in the same line, but okay. Yes.
I'm wondering, what is the percentage improvement? Is it like significant for people that use these type of approaches, or?
So the improvements over cart are like kind of already. So this is like cart is like it's a very powerful heuristic,
Okay.
right? And improving over that is already very hard. And so this, or at least these are like the small data sets. And Firat and other people compared it with the models that actually generated the optimal trees, and they were comparable to that, right? So my the updated gains are still not optimal, but they are still like very much comparable. So in that sense, like yeah, the optimal, like there's not much to gain when you come to like even when you try to generate even the optimal decision trees. But these are like we're coming very very close to that.
Yeah. But I guess my question is, so for the people that use optimal decision trees, is there an interest to switch to not using cart or not?
I don't know actually. But it's like there is now a way if you don't want to stick to cart, and within just 10 minutes you can do something slightly better. If you have more extra 10 minutes, then maybe do that. Yeah. Okay. Yeah.
Is the paper on archive or other?
I'm writing it. Too early.
Can I have it now?
I haven't written. Still writing it. Yeah.
1, 2, 3. How about now?
My impression is that the beta constraints are important, but they're difficult to handle. Is that
They are like depending on, so like if you have very very large data set,
Yeah.
then you have very very large number of constraints, right? So that's why it's kind of, it's not difficult to handle, but it's just that makes the LPs larger, and that's why it like slows down the process.
Have you thought of having surrogate constraints, so aggregating them in groups, and so still including them in the master, but kind of aggregated them, and to have the best of both worlds?
No, I don't think I considered that part. Maybe I will, but so partly like we are already removing duplicate rows, but other than that, I'm not sure it's easy to aggregate them. And secondly, it's like already we are adding them as cuts, right? So only when they are violated. So it's kind of
So you show that you were able to solve to optimality some of the instances because you got the integer solution, I think, at the root node.
So when I say optimality, it means like for the restricted problem, not for the overall optimal tree.
Okay.
Yeah.
And so with the same approach, did you measure the integrality gap that you had on the other instances?
I didn't measure the integrality. When you say integrality gap, means the variables taking integer values, or the gap in the optimal LP value and the objective integer objective value.
So the gap between the solution that you report here and the LP solution that you got at the root.
So Optimality means.
The MIP that
Oh,
you
so
solved,
the cases where I didn't solve it to optimality, that's what you are asking. I think they were very, very small. Yeah, I haven't reported it, but like those gaps were very, very small. Yeah, and those other experiments were done on the depth of T depth of 4. But yeah, so that was like the hardest of all these experiments, because the other lower depth trees are like easier. They are very, very easy to reach optimality even in this, or even like the easier variants. Yeah. So yeah, the gaps are small for when I don't prove optimality.
But they are small comparing to your gain, or they are just.
Yeah, so the gains are similar, right? For these other 4 variants, it's not really big differences in terms of gains. I didn't measure the effects on 600 seconds, but like when I run it without time limits, they're roughly the same gains. It's like the optimality is like kind of a thing that we don't need to care about in this setting. We care about it, but yeah, we don't need to.
I think that we have to stop here. We are 10 minutes late.
C'est intéressant de
We have to
savoir.
move.